So this was the question that we were actually, I think, on, that which reaction is most likely to involve the formation of a positively charged intermediate. So I think we had started talking about SN1, SN2 reactions, which was nucleophilic substitution. So let's just go back quickly. We did this, and we did talk about the mechanism as well. We talked about the mechanism of one of the reactions. So let me just quickly go through this. So we talked about halogenoalkanes. I told you that you have a halogenoalkane when you have a carbon chain which has a halogen attached to it. And the halogens are polar. So the carbon CCl bond is going to be polar. And there were 3 nucleophilic substitution reactions. One of them was hydrolysis, that the Cl could be changed or substituted by an OH. It could be substituted by an NH2, or it could be substituted by a CN. So NHCN ethanolic, NH3 in gas form, or NH3 ethanolic, or you can hydrolyze it, which is NaOH aqueous, and reflux. So we talked about these reactions that you can substitute, and these were all nucleophilic substitution reactions. And we also talked about how this reaction would happen. We talked about the mechanisms. I told you that the nucleophilic substitution mechanism depends on what type of halogenoalkane is it. Is it a primary, secondary, or tertiary halogenoalkane? So for primary halogenoalkanes, we talked about this mechanism, that how will the OH ion or the NH3 molecule or the CN-1, how are they going to substitute the Cl? So we figured out that the way they're going to do that is, so the way, one second. So the way they were going to do this is that I told you that the OH-1 nucleophile is going to be attracted to the carbon, which is positive, and the electrons in the Cl will be repelled. So the electrons in the Cl will start to leave. The OH ion would come in and will get attracted to it. Eventually, the OH would join with it, and the Cl would get knocked out. Is that clear? This one.
Yes.
And then you have another mechanism, which is for tertiary halogenoalkanes. Now, what happens in that scenario? So if I have a tertiary halogenoalkane, what will happen in that? Tertiary halogenoalkane is that the alpha carbon would be bonded on 3 sides by carbon chains. So it's going to have CH3, it's going to have, let's say, a CH3-CH2 chain. And it's got another. Anyways, it's got another CH3. So the carbon is slightly positive. The Cl is slightly or partially negative. And you've got these nucleophiles coming in. So 3 nucleophiles. It's either going to be OH-1, or it's going to be the other ones, CN-1, or the last one, which is NH3. So 3 nucleophiles. Now, what will happen in this case is that initially the nucleophiles are not doing anything. So initially, right at the beginning, the nucleophiles are not doing anything. The Cl bond breaks on its own. The carbon and Cl bond, it breaks on its own, and a carbocation is formed. So the Cl leaves, and you get this carbocation. The Cl has left, the bond has broken. So it's no longer slight positive or slight negative. The Cl has taken both electrons with it. So it's -1, and you've got anyway, so it's -1, and the carbon over here is positive. So this is a carbocation intermediate. So that's a carbocation intermediate. So that's first step number 1. Once this step takes place, then the nucleophiles, they come in. So you've got your OH minus 1 coming in with its lone pairs, and they're going to come in and they're going to get attracted to the carbocation. So it could be any of the other ones as well. It could be NH3. Its electrons can get attracted to it, or it could be your CN minus 1. So all of these would come in the next step. So not in the first step. In the first step, they don't have anything to do with it. And they're going to come in and they're going to join up. And when they join up, the Cl will get substituted. So it's going to end up forming. So you had, let me just copy this. So anyways, this OH comes in and joins up. And you've got an OH that has joined up. So the reaction is slightly different from the first one. Now it's a two-step reaction. Remember, this one is an intermediate, which means that this thing is actually formed. This is step 1. So it's a proper two-step reaction. This is step 1, and this one is step number. So this one is step number 2. And it's a proper two-step reaction. So this over here is a two-step reaction. So there's one major difference. Primary halogenoalkane, everything happens in one go. The Cl gets knocked out and the OH comes in and joins at the same time. The only difference over here is the Cl gets knocked out first and then the OH comes in and joins it. So there's one minor difference and a carbocation is formed. Is this clear? Are the two mechanisms clear?
Yes.
I said, now there's another question. So why is this happening? Why does one undergo, and this is known as, the tertiary halogenoalkane mechanism is known as an SN1 mechanism. So it's nucleophilic substitution, but it's SN1. Let me write it the same way. It's the way it's written in the paper. That's S, capital N, and then 1. So it's an SN1 mechanism. So the question is, why is this happening? So the answer to that is, so this is the question that's going to be asked, which is, why do primary halogenoalkanes undergo SN2 mechanism? So why do they undergo SN2 and vice versa? Why do the other ones? Why do they undergo SN1? So and tertiary undergo SN1. So the answer to that is, I mean, the answer that you're going to give to Cambridge is that primary halogenoalkanes, so these ones, the answer to that is that they have fewer electron donating alkyl chains. So they have fewer electron donating alkyl chains. Hence, the carbocation formed is very unstable. Sorry, yes, and hence the carbocation, yes. Hence the carbocation formed is unstable. Now, you still will not be able to understand what this means, but that's the answer. That's the answer that you're going to write. And I'm going to explain this. And why do tertiary undergo SN1? because they like to form carbocations. I mean, that's the basic answer, but I'm going to go into a bit more detail. Right now, let's just write what the required answer is. So why do tertiary? Because they have more electron donating alkyl chains. So they have more electron donating alkyl chains. Hence, tertiary carbocations are more stable. Now that's the word answer. Now let me explain this first. What's the difference between primary and what's the difference between tertiary? Primary, the Cl leaves only when the OH comes in. The OH -1 comes in and the electrons, they get repelled, and then the Cl leaves. Tertiary, the Cl leaves before the OH. Cl leaves, carbocations formed, and then the OH comes in. Right? That's the major difference between a tertiary halogenoalkane and a primary halogenoalkane. So why is that? So the reason for that is, let's think, and this is just the explanation of what we just wrote. So, I mean, your answer should be the one that's written over here. But this is just the explanation of how do you understand this? Like, why would primary halogenoalkanes? So let's draw a primary halogenoalkane. It's got one carbon chain. So let's imagine that the Cl, it breaks away, right? And at the same time, I have a tertiary halogenoalkane. And in that case as well, let's imagine that the Cl, it breaks away, it takes away both electrons. So the Cl has broken away. This has become positively charged carbocation. This is -1. Over here as well, the Cl has broken away, taking both electrons. So this is Cl -1. This is the positively charged carbocation, right? Now what happens is, if you focus on this, both carbons have a positive charge. Whose positive charge do you think is greater? This one or this one?
The first degree.
The first degree, would that be greater? I mean, so then remember that's a primary carbocation or first degree carbocation. It's going to be greater. So this positive charge is actually going to be greater or larger. And this one over here is going to be, it's going to be smaller in size. What's the reason for that? Why is this smaller? Yes, Mikhail.
The surrounding carbons come close to decrease the positive charge.
Okay, so basically it's got, I mean, the positive charge is right in the middle of the molecule, and it's got these large groups attached to it, right? So these large groups have a lot of electrons. Like carbon has 6 plus there are 3 hydrogens, so that's a total of 9 electrons here. Yes, Mikhail.
Oh, I forgot to put that hand up.
Okay. So the point is that the carbocation is formed right in the middle of the molecule. So it's surrounded by large groups. So there's 9 electrons on top. I mean, carbon has 6, 3 with hydrogens. That's a total of 9 electrons over here. 9 electrons over here. 9 electrons over here. So that's a total of 27 electrons that are surrounding it. So imagine there's a positive charge right in the middle of a lot of electrons. So what will happen? The electrons will get attracted to the positive charge, and the positive charge will kind of get neutralized. It's going to be a lot smaller. Is that clear?
Yes.
So why is this larger? Because it doesn't have 27 electrons around it. Like it's got one carbon chain. So that one carbon chain has how much? 9 electrons. But on the other side, it's got just hydrogen has 1 electron. This hydrogen also has 1 electron, right? So this carbon, which is a carbocation now, it's not surrounded by 27 electrons. It just barely has 11 electrons around it. And even those 11 electrons belong to other atoms, right? So even if the positive charge wants to attract those electrons closer to it, there's just not enough negative charge going around. Is that clear?
Yes.
So the positive charge, is not going to be neutralized, and it would be relatively larger. And over here, the surrounding neighborhood. So remember this: tertiary carbocations or third-degree carbocations have lower charge density. So they've got a lower positive charge density. And meanwhile, primary carbocations, they always have a higher positive charge density. So let's link it up with the mechanisms now. Why does the mechanism change? The reason why the mechanism changes is that in primary carbocation, it would be very hard for the Cl-1 to take away both electrons. Now, if you have a Cl-1 and the Cl-1 wants to leave, the larger positive carbocation would be holding it close to it. It will be attracting it. So this bond would be harder to break. Is that clear?
Yes.
And over here, the Cl could easily leave with the electrons. Why could it do that? Because the positive charge is a lot smaller. So the positive charge of the carbocation is not going to attract the Cl-1 back again. Is that clear?
Yes.
So tertiary carbocations, or the formation of tertiary carbocations, is a lot easier. The formation of primary carbocations is slightly more difficult. Like if this Cl wants to break away, it would be kind of hard for it to go away because the larger positive carbocation would be pulling it close to it. So the bond is a lot stronger over here, and the bond over here is a lot weaker, which is why in tertiary carbocations, where's the tertiary one? In tertiary carbocations, usually the Cl breaks away first, and then the OH-1 comes in. Is that clear?
Yes.
And in that case, the other one, because it's harder for the Cl to leave. So in this case, in primary carbocations, they're not going to be formed because they would have to wait for the OH-1. The OH-1 is going to come in. And because of the OH-1 approaching it, then the Cl will get knocked out. So the OH-1 would come in, and then the Cl will get knocked out, because otherwise it would be very hard for the Cl to leave because there's a very strong positive charge. Is that clear?
Yes.
Okay, so that's the explanation, and there's another reason for that, and that is the shape, because if it's surrounded by large groups and the carbocation is in the middle, the nucleophile, which is the OH-1, is not going to be able to approach the carbon because the carbon is right in the middle. Is that clear?
So I don't understand.
No, there are large groups around it, right?
Yeah.
So imagine an OH-1 trying to come close to the carbon, right?
Yeah.
So because it's, I mean, let's think of it over here. So this one. So because it's surrounded by large groups, and there's an OH-1, let's say over here, it will not be able to come close to the carbon because it's surrounded by big groups. Is that clear?
Okay, understood.
But in primary, the OH could do that because the carbon is very exposed. Hydrogen atom is like nothing. It's not even it's just got one proton. So it's not surrounded. It's pretty open. The positive charge is like really out there, and the OH-1 could come easily to attack it. Right? Is that clear?
Yes.
Yes.
Okay, so that's the mechanism that you have to remember, that you've got a primary halogenoalkane, and you've got which is SN2 mechanism, and then there's a tertiary halogenoalkane. More carbon chains, you get a more stable carbocation, so it's a lot easier to form a carbocation, and the Cl-1 would therefore decide to break early. and then they can wait for OH ions to come in. And remember the explanation. The explanation that you're going to give is if you have fewer electron donating alkyl chains, it's going to be hence carbocation formed is unstable. More electron donating alkyl chains, the carbocation is going to be more stable. And you can also add about charge density. So higher positive charge density, and the other one is lower positive charge density. Now, so that's pretty much it. Now the next question is, what does 1 and 2 mean? What's SN2? I mean, what does it mean? Anyone, any idea what does SN? I mean, we know what SN is. What is 2? कोई idea, Muneeb? Anyone, Mikal?
Is it like 1 means 1 step and 2 means 2 steps?
No, but 2 is the one which has 1 step actually. So
was it something to do with what rate, like which rate?
It's linked with rate. What 2 means is that the rate depends on both reactants. That is the meaning of 2, that it depends on both reactants. So rate depends on the halogenoalkane and it also depends on the nucleophile. So if you increase the concentration of the halogenoalkane or you increase the concentration of OH-1, the collisions would increase and the rate of the reaction would increase. So rate depends on both reactants. Is that clear?
Yes.
Now 1 means the rate depends only on the halogenoalkane. So 1 over here, not on the OH ion. So over here, 1 indicates that rate depends on halogenoalkane concentration, and it doesn't depend on the OH-1 concentration. So the question is, why is that? And the answer to that is, when you have a 2-step reaction, not always, but when you have a 2-step reaction, what happens is one of the steps is faster compared to the other one. So let's say the first step is a slow step that's taking 100 seconds. And the second step is a fast step that's taking, let's say, 1 second, right? So I've got 2 steps. The Cl leaves in the first step, and then the OH comes in and joins with the carbocation. Now the question is, why does the rate depend on one of the reactants? You have 2 reactants, right? You have a halogenoalkane, you've got the OH-1. Now think of this. If I increase the concentration of OH ions, like by a big margin, which of the 2 steps would speed up? The first one or the second one?
The second?
The second one.
Okay, because OH ion has nothing to do in the first step, right? So if you increase the concentration of OH ions, there's going to be a lot more OH ions and the reaction would be a lot faster because there's going to be a lot more collisions. So the reaction would happen more quickly. So let's say it happens more quickly. It's taking 1 second right now. And if I add more OH ions, it's now taking, let's say, 0.01 seconds, right? So if I speed up the fast step, this one was already fast and I've speeded it up even more. What happens to the overall speed of the reaction? It's taking 101 seconds, right? So even if I increase the OH ion concentration by a big margin, the overall speed of the reaction will not be lesser than 100 seconds. Like you can speed it up from 101 to 100, right? Right now it's taking 101 seconds, right? No matter how much you increase the concentration of OH ions, it would be impossible for the reaction to speed up, and the time taken will never go below 100. Is that clear?
Yes.
So that means OH isn't really helping. Like even if you increase the concentration of OH by 1,000,000 times, the overall speed of the reaction would kind of be still the same. So that means the rate is not dependent on the concentration of the OH. Is that clear?
Yes.
Yes.
And that's a rule. You'll study that in A2, but the rule is that anything that's involved in the fast step, the rate of the reaction is not dependent on that. So think of it as a relay race. If there's a relay race going on, let's say there's 3 fast runners and there's 1 slow runner, right? So you can't speed up the overall time by changing the faster runners or speeding them up. It's the slow runner that's the one that's causing the delay. So basically, if you want to speed this reaction up, you have to speed this up. So if I change the halogenoalkane concentration, if I double it, the reaction would be, let's say, twice as fast. And instead of taking 100 seconds, it's now taking 50 seconds. So the overall speed of the reaction is now going to be much faster. Is that clear?
Yes.
Yes.
So that's the basic idea between a 1 and 2, right? And you've got another one, which is secondary halogenoalkanes. We'll just write a point about that. Secondary halogenoalkanes, they undergo a mixture. It's like a mixture of SN1 and SN2. Because their carbocation stability is kind of in the middle.
So this question, why do primary halogenoalkanes undergo SN2 and tertiary undergo SN1? Can this come up in the exam?
Yes, that's why I wrote that. I mean, that's,
Oh.
I mean, you're not going to give this explanation. This is just for your understanding. The explanation that you're going to give is this. That, I mean, they're going to ask you, why do primary halogenoalkanes undergo SN2? Because they've got fewer electron donating alkyl chains. Hence, the carbocation formed is unstable. So it's very hard to form that carbocation. And it's got a higher positive charge density. That's about it. So,
All right.
so primary, the positive charge is going to be larger. So it's not going to let go of the Cl until the OH-1 comes in and pushes it away. Tertiary, the more electron donating alkyl chains, so the carbocation is a lot more stable. The positive charge density is lesser. So if the Cl-1, even if it decides to lose, it's not going to attract it back because the positive charge is not that strong. So this will come in the exam. That's why, I mean, these two things. As anyways, coming back to the question now. So the reaction, he's saying, one second. So the question states, which reaction involves a positively charged intermediate? So that means a carbocation, right? So it must be a tertiary halogenoalkane, right? Is that clear?
Yes. Yes.
So I said this must be a tertiary halogenoalkane. So this is all correct that you have to warm it with dilute NaOH, right? Because OH-1 nucleophile, right? I mean, this is what we studied. Like if you want to do nucleophilic substitution, then it's NaOH aqueous and reflux. The mechanism, the question is about mechanism. So which one is the tertiary? Because positively charged carbocation intermediate, that is an SN1 mechanism. So that is tertiary. So which one is tertiary? 1-bromopentane, is that tertiary? Pentane is 5 carbon atoms. That's 1, 2, 3, 4, 5. 3. And there is 1 bromine. Which one is this? Is this a primary halogenoalkane or a secondary or a tertiary?
Primary.
Okay, so we're not looking for primary. So the first one is wrong. Then you have propane, right? So draw propane. So we're going to start with propane. Propane is 3 carbon atoms, right? And it has 1 bromo 2,2-dimethyl. So 1 bromo. Let's put a bromo. And 2 and 2 dimethyl. So 2, 2. So that means 1 carbon atom, and there's going to be another 2, 2 dimethyl propane. So this is methyl is 1 carbon atom. So 1 carbon atom. Which one is this?
Tertiary.
Need this one. The focus is on the alpha carbon. How many carbon chains is this attached to?
One.
Oh, one. Okay.
So it's primary, right? Let's do the other one. Butane, 1 bromo 3 methyl. This one, 1 bromo 3 methyl butane. So that one is butane is 4. So 1, 2, 3, and 4. And 1 bromo. So there's a bromine on the first one, and 3 methyl butane. So third one. Third one is a methyl, or it's just got a carbon. So which one is this?
Still
Primary.
primary.
Still primary. So we're down to the last one, right? It was 2 bromo, 2 methyl butane. So 1, 2, 3, 4. And then it's 2 bromo and 2 methyl. So bromine is attached to this one, and methyl is also attached to. So which one is this one now? The alpha carbon.
Tertiary.
Tertiary.
That's a tertiary one. So that's going to form a carbocation. It's going to form a carbocation first. The Br would leave, and then the OH minus one would come in. Is that clear?
Yes.
So the last one is the correct option. Now, infrared spectroscopy. It's let me just quickly check. Is it still there, or 1 second? So carbon 13 HNMR. No, that's HNMR. We're talking about carbon infrared. So this is, yeah, but which? Molecular mass. Okay, so A level starts after this. So this is it. So fine, you've got infrared. So I'll just quickly discuss. Infrared is kind of really easy. No need to go into a lot of detail with infrared. Where's the paper? Now here's an infrared spectrum. Do you know what an infrared spectrum is? Anyone, any idea? Yeah, have you studied this?
Uh,
No.
oh,
Okay, it's
No,
so
sir.
it's a very small concept. It's just that you see all these bonds, right? I mean, like if I show you a molecular model, a molecule has in 3-dimensional, so molecular model of, let's say, ethane. So it's got lots and lots of bonds at different angles. So maybe this one's a good one. So this is like an ethene model, right? So these bonds are, it's trigonal planar, it's fan shaped. But remember, the bonds are not like all of these bonds, they're not rigid. What I mean by rigid is that they vibrate and they swing. So they're not stuck exactly at one place. I mean, this bond over here would sort of vibrate to and fro. Is that clear?
Yes.
Just like if there's a piece of wood on a tree, there are branches in a tree, right? So the branches are always swaying around. Okay, they're like, and why do they sway around? Because they gain energy from somewhere. Like if there's wind, the branches would sort of swing and they would move up and down, to and fro, in all directions, right? Is that clear?
Yes.
So for the bonds to sort of vibrate and fluctuate and sort of stretch and compress, they need energy. Some sort of energy would be gained by them, and that energy is gained from the infrared spectrum. Infrared is a spectrum of the radio waves, and not a radio wave, it's electromagnetic waves. So you gain energy from infrared waves, and they're going to gain a very specific amount of energy. For example, they're going to gain a very specific frequency of energy. For example, there's a swing, right? The swing, like when it starts to swing, like if there's a park and there's a swing, it gains energy, right? When you push it, it gains energy and starts moving and starts swinging just like a tree branch. Is that clear?
Yes.
Now the question is, do you think you can give energy to the swing at any frequency, or do you have to give it at a very specific frequency? Like imagine there's a person sitting on a swing and you have to push him from behind. Can you just randomly start pushing him and hitting him randomly, or do you have to give the energy at a very specific frequency in a very timed way?
In a timed way.
Timed way.
Yeah, so it's basically when you time your pushes, so that's basically a frequency, right? A number of times per second, right? So basically, and that's the same with these bonds over here. Think of the bonds as these tiny swings that would vibrate, but they're not going to vibrate at any random frequency. They will absorb a very specific frequency. Every swing is different, right? Like some swings are really big, so the timing has to be different, right? You have to push the person at a different time interval, right? So the frequency keeps changing. So in the same way, every bond is different. Every bond has a very specific frequency, and they're not going to absorb any frequency. Like if infrared spectrum particles from the infrared spectrum, photons from the infrared spectrum, they hit this, it has to only absorb a very specific frequency. It's not going to swing at any frequency. Is that clear? Is the idea clear?
Yes.
So in your data booklet, you're given these frequencies. Hopefully this one is, not sure if this is a data booklet, but wait a second, infra. So this is your data. I mean, this is ionization energies, and those are your bond energies. Electrode potentials. Where's infrared? I think this one. No, that's an HNMR. That's not in your course at the moment. After this, probably. No, not this one. There's going to be a table. They're going to give you a table now. So this is infrared frequencies. So it's given for all the different bonds. The frequency is given. Like C, if the CO starts to swing, stretch, and compress, the bond would absorb frequencies from this range, 1040 to 1300. Wave number is simply 1 over lambda. I mean, what is 1 over lambda? That's proportional to frequency, right? Does everyone know that? 1 over lambda is frequency, right? Or proportional to frequency. I mean,
No, sir, I haven't taken it yet.
Nate, do you know what V is equal to lambda F, right? Do you know that?
Yeah.
Now, velocity is constant. Like for electromagnetic spectrum, the velocity is constant, right? So V over lambda would be equal to F, right?
Yeah.
So what's the relationship between wavelength and frequency? It's this relationship, right?
Yeah.
So frequency is proportional to 1 over lambda. So wave numbers are basically 1 over lambda. You don't have to know that, but just remember this is proportional to frequency. Is that clear?
Yes.
So I mean, these numbers, think of them as frequencies. So every bond is absorbing. The double bond vibrating would vibrate at this frequency. The double bond O vibrating would vibrate at these frequencies. The triple bond N would vibrate at these frequencies. So all their frequencies, absorption frequencies are given. And you've got to, are there any others? Just a second. Yeah, I don't think there's, no. So those are the only bonds that are given. Now, one of the frequencies are really easy to figure out. Some of them. One of them is serial bond O. It's really easy to spot. There's going to be an absorption at the 1600, 1700 range. A lot of molecules have serial bond O. The amides have serial bond O, carbonyl, ketones, aldehydes, carboxyl group, ester. They all have serial bond O. Carboxylic acids have serial bond O. So whenever the serial
Sir,
bond
do you
O,
have to know this, by the way, or will it be given in the question?
no, that's going to be given in the question.
Okay.
And then there's this one. You have to know this, like when you're studying the infrared spectrum, you can't really figure out all the bonds, but two bonds you can always figure out very easily. Serial bond O, because that's a unique absorption range, right? And the OH as well. It's a pretty unique 2500 to 3000 or 3600. There are two types of OH groups. One is a carboxylic acid one, so that's 2500 to 3000. The other one is a hydroxy, like a simple OH. So that's 3200 to 3600. So let's just quickly have a look at this molecule. The rest of the stuff is kind of easy. Like if you have a look at this, where's the molecule? One second. So if you have a look at this molecule, there's a pretty strong, the dip is the absorption. So there's a pretty strong absorption at Y, around the 1600 range, right? So go back, 1600 range, what did I tell you? That's serial bond O, right? Is that clear?
Yes.
Yes.
So pretty easy to spot serial bond O. And then there's an absorption around the 3000 mark. And that absorption is, so what is that 3000? Now for that 3000, it could be a CH with 50 to 2950. Could be an OH from the carboxylic acid, but we're not sure. And who else? I think it's just this and this one, right? The OH and the CH. So the competition is between the OH and the CH. So now this particular question, they've actually changed this. I mean, the new syllabus has changed this. Let me just quickly, just give me 1 minute. Let me open the old data booklet for a second. Because they've kind of simplified it. So the questions I'm assuming would also be simplified. Because the syllabus data booklet that they now have is a lot simpler. I'll tell you the previous one. It's something similar, but they give you an extra information as well, which is in the new syllabus, this thing is missing. This thing, the appearance of the peak, that's missing. So if that is missing, then obviously the question is not going to be that detailed. So remember, we had a peak at 3000, and now if I go back to the question, look at the shape of the peak. It's a small peak, pretty sharp, and it's not very strong. So this one we've already figured out, that's serial bond O. This one is a relatively small peak. So you're going to open this data booklet, opening the old one. Around the 3000, it's not a strong and very broad peak. So that's out of the question. And it's not, so that is out of the question. It's not a carboxylic acid. It's a CH peak because it's a weak, so it must be around, the CH might belong to an alkene or it might belong to an alkane because both of them have CH bonds. So it's a kind of a weak peak around the 3000 range. Is that clear?
Yes.
So W stands for weak. But now, obviously, the new syllabus does not have this column. I mean, the data booklet that they gave does not have this. So I think the questions would therefore have to be a lot simpler because you couldn't answer this question using the new one. So this one is CH. Because if it had been OH, it would have been strong and very broad, which it isn't. So is this clear?
Yes.
This one is serial bond O. So infrared spectroscopy is pretty easy. So I'll just sum it up. Bonds vibrate and they fluctuate. So they've got you've got a data booklet. This thing is now missing. The shape of the peak is missing. The different wave numbers, they would the bonds would absorb those frequencies. So you just have to match. The easiest ones to figure out is Seidel bond O and the OH. Those are the easiest to figure out. In this case, in this particular case, this was not OH. OH had a strong and very broad peak, which it's not. It's a very weak peak. So it must be CH. Chale, let's continue next time. Okay.
Okay.
Okay, sir. Assalamu
Okay, sir. Assalamu
Okay.
alaikum.
Assalamualaikum.
alaikum. Sir, wait, I have a question.
Yes.
So we have our exam on Thursday. So do you have any tips or anything?
You have the complete exam.
No, it's like I think until Carbo.
Tell me
It's
the
mainly on organic chemistry.
it's just
Until
mainly
carbon.
send it on WhatsApp. Send me the topic. Like if it's the whole organic chemistry or just a few topics.
Yeah,
Okay.
okay, I'll tell you.
Sir, can we do the Thursday class tomorrow? Just for this
Sure.
week, maybe.
Sure, we can do that.
Yeah, okay. So,
We can have a longer class if you want. Okay.
All right.
Okay.
yeah, okay.
Okay,
Take-
sir. Allah Hafiz.
Enough.